Hi, everybody. This is Miss McClellan here to go over the practice FRQs for your Unit 4 AP Stats test. Here we go. Problem number 1. Show all of your work. Indicate clearly the methods you use because you will be scored on the correctness of your methods as well as the accuracy and completeness of your results and explanations. This problem says that at a financial institution, a fraud detection system identifies suspicious transactions and sends them to a specialist for review. The specialist reviews the transaction, the customer profile, and past history. If there's sufficient evidence of fraud, the transaction is blocked. Based on past history, the specialist blocks 40% of the suspicious transactions. Assume a suspicious transaction is independent of other suspicious transactions. Okay, part A. Suppose the specialist will review 136 transactions in one day. Suspicious transactions. What is the expected number of block transitions by the specialist? Show your work. All right, let's see. This, I'm going to name my random variable. Let's let x equal number of blocked suspicious transactions in a batch of 136. First of all, x is binomial because I have a fixed number of trials. I have independent trials. I have binary either success or failure. And I have the same probability of success in every trial. So it's binomial with a probability of success 0.4 and number of trials 136. Since it's binomial, the expected value has a formula we can use, which is n times p. So that's 136 times 0.4 equals 54.4 blocked transactions. You might think you're done, but you're not. This question didn't ask you to interpret the results in the context of the problem, but you always have to interpret your results in the context of the problem, so we still need to do that. Okay. The specialist can expect to block 54.4 suspicious transactions per day. Well, we'll say per 136 suspicious transactions. In the long run. Period. Next problem. Part B. Suppose the specialist wants to know the number of suspicious transactions that will need to be reviewed until reaching the first transaction that will be blocked. I see the word until. I know, and I see that it's number of, so this is going to be geometric. So let me define this random variable. let's let y equal the number of suspicious transactions the specialist will review until they block one. And y is geometrically distributed, and the probability that any given suspicious transaction will be blocked is 0.4. So determine the expected value of this random variable. Well, since it's geometric, the expected value of y is 1 divided by 0.4, the probability of success, which is gives us 2.5. In context, we say that the specialist can expect to block an average of 2.5 transaction. Oh, sorry, I'm saying this wrong. The specialist can expect to review an average of 2.5 transactions until they will block one. And this is after many trials, as in, this is just an average. I think the last sentence I put in makes it kind of confusing, so I'm just going to take that out. Okay. Part C. Consider a batch of 10 randomly selected suspicious transactions, and suppose the specialist wants to know the probability that 2 of the transactions will be blocked. So this is going to be a binomial random variable, because I have binary outcomes. You could either be blocked or not blocked. Independent trials given in the overview of the problem, a fixed number of trials, 10, and the same probability of success for each trial. And I'm going to define a random variable as the number of transactions blocked in a batch of 10 randomly selected suspicious transactions. And I note that Z follows a binomial distribution with probability of success 0.4 and number of trials 10. And we're going to find the probability that 2 transactions in the batch will be blocked. So I want to find the probability that Z is exactly 2. And that is to choose 10 times 0.4 squared times 0.6 to the 8. And if you do that, you should get 0.1209. Or you could show your work by doing binomial PDF with n equals 10, p equals 0.4, and x equals 2, which will also get you 0.1209. Done with that problem. On to problem 2. Show all of our work, indicate clearly the methods that we use, because we will be scored on our correctness, blah, blah, blah. Okay, Miguel is a golfer, and he plays the same course each week. The following table shows the probability distribution for his score on a particular hole, known as the water hole. Let x be the random variable representing Miguel's score on the water hole, and remember or know that in golf, lower scores are better. It's nice that they defined a random variable for us. Suppose one of Miguel's scores from the water hole is selected at random. What is the probability that Miguel's score on the water hole is at most 5? So we want to know the probability that x is less than or equal to 5, and that equals the probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5. And from our table, we just have to add those probabilities up. 0.15 plus 0.40 plus 0.25 equals 0.8. And we need to calculate and interpret the expected value of x, and we'll show our work. So the expected value of x, by definition, is going to be equal to the scores multiplied by their respective probabilities and then all added together. So 3 times 0.15 plus 4 times 0.40 plus 5 times 0.25 plus 6 times 0.15 plus 7 times 0.05. And if you put that in your calculator, you get 4.55. And let's interpret that. We expect Miguel to get a score of 4.55 on average in the long run. Or if you could also say, if he plays the hole many, many times, we expect him to get an average score of 4.55 on this hole. Okay. The name of the water hole comes from the small lake that lies between the tee, where the ball is first hit, and the hole. Miguel has 2 approaches to hitting the ball from the tee: the short hit and the long hit. The short hit results in the ball landing before the lake. The value of x in the table are based on the short hit. The long hit, if successful, results in the ball traveling over the lake and landing on the other side. The 2 approaches are shown in the following diagram. A potential issue with the long hit is, what if it lands in water? That's not a good outcome. Miguel thinks that if the long hit is successful, his expected value improves to 4.2, which is better than 4.55. But if the long hit fails, then he expects a lower score. Oh no, 5.4. So suppose the probability of a successful long hit is 0.4. Which approach, the short hit or the long hit, is better in terms of improving the expected outcome value of the score? So let's let z equal the expected outcome value of the score. Then z is distributed as he makes the shot and the expected score becomes 4.2, or he misses the shot and the expected score becomes 5.4. And the probability of each of these outcomes, as given in the problem, is 0.4 and 0.6. And we want the expected value of the scores, which is expected value of z equals 4.2 times 0.4 plus 5.4 times 0.6, which is 4.92. Let's justify. Okay. Let's make a conclusion and justify it. So this is a higher score since 4.92, which is EZ, is greater than 4.55, which was E of X. E of X has the better expected score. So the short hit is better in terms of improving the expected value of the score, since lower scores are better in golf. Okay, now let P represent the probability of a successful hit. So before we had P equaled 0.4, but now it's just P. What value of P will make the long hit better in the short term? Let's redo the distribution of Z. So now we have Z still. Z could be 4.2 or Z could be 5.4. And then the probability of Z is now just P or 1 minus P, which gives us that the expected value of Z has become 4.2 P plus 5.4 times 1 minus P. And let's see, we want to make the long hit better than the short hit. The long hit is better for improving the score if the expected value of Z is less than the expected value of X. Now this is 4.55 and this is 4.2 P plus 5.4 times 1 minus P. So we're going to set up an inequality and solve it, where we have 4.2 P plus 5.4 times 1 minus P is less than 4.55. Here we go. 4.2 P plus 5.4 minus 5.4 P is less than 4.55. I have to subtract 5.4 from both sides. I have negative 1.2 P is less than, 0.85, and that's a negative value. I don't want to deal with negatives, so I'm going to flip this around. I'm going to add 0.85 to both sides, and I'm going to add 1.2p to both sides. That gets me to 0.85 is less than 1.2p. Then I'm going to divide both sides by 1.2p. And that gets me that p is equal to, sorry, p is greater than, not equal to, strictly greater than 0.708, which means that if p is greater than 0.708, then the expected value of the score for the long hit is better than the expected value of the score for the short hit. That's the end. Okay. Thanks for following along. I'll post a video of the other practice as soon as I can. Thanks, everybody. Bye.